Okay, in this video, I'm going to be talking about op amps. Um, I'm going to be talking about op amps, voltage followers, and voltage comparators. So, op amps, okay. An op amp is a component that has one output and two inputs, and this is its general form. So you can see there's a triangle, there's a plus and a minus, right? And then the two inputs and then one output. And then this input is called V plus, this input is called V minus, and then this output is V out lah. So generally you will see it like this. And what it does, right, is it reads the voltage at the two inputs, and then it does this equation here to get the output, the output voltage. So basically it inputs a few voltages, and then it goes to itself, okay, what am I going to do now? Then after that, it outputs a certain voltage. Yeah. And then, and the equation is this lah. So there's this thing AOL. This actually stands for open loop gain. So with every op amp, right, it has an open loop gain. Ideally, that means like not in a practical sense. The gain is supposed to be infinity. like 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 infinity lah, like this. That's ideally, but in a practical setting, most of the time it's like a very very high number, like 100,000. Yeah. So so the gain for all or most practical op amps like in real life is around 100,000 or more. Okay, so yeah, every op amp has an open loop gain, and then what it does is we take the difference of V plus and V minus, and we multiply that with the open loop gain, and that gets us V out. So let's run a simple scenario lah. Let's say at V plus there is 6 volts, and then at V minus there is 4 volts. So and then let's say that the open loop gain is 100,000 lah. So what is the V out lah? So we can calculate this. It'll be like this, 4 volts. Okay, then where's my calculator? Okay, then we can just calculate this, and then we get 200,000 volts. I could have done that in my head, never mind. Okay, so in this case, right, the output of this op amp is 200,000 volts. So think about that for a moment. Does that make sense at all? Nah, it doesn't. You're putting in 10 volts, because 6 volts at V plus, 4 volts at V minus, right, into this magical component, and then with nothing else, it just churns out 200,000 volts. No, it doesn't work that way. So this is, we are half done. This is the base form of an op amp, but actually you will also see them commonly like this. So we got the triangle, and then we got the two inputs, the one output, right, the plus minus and all that crap. But we got actually two more inputs, or two more pins in the op amp. We actually have this and this. So this is probably going to be familiar, but basically this is VEE. So this is we're actually powering this chip, and this is another chip which I forgot the name of. I'm gonna go and check that out now. But basically what it does, right, is like, basically it's like it's like clamping. So what do I mean by that? This is this is VCC, and then this is VEE. So as I mentioned, it does something like called clamping. So what I mean is this. So in here, right, let's add this into this op amp actually. So let's say our VCC is 5 volts, and let's say our VEE is ground, which is 0 volts. Okay, ground is 0 volts. So now we look at this. As I said, clamping already. So theoretically, it's supposed to be 200,000 volts, but it's being clamped by the 5 volts. You understand what I'm saying? So if I were to draw a graph, I'll draw a graph of voltage over time. Yeah, okay. It is actually clamped by 5 volts here and 0 volts here. So right now, right, our output, like let's say we power it on now, our output is theoretically at 200,000 volts, but it's being clamped by these 5 volts here. So blue, which will signify the actual output, will be clamped at 5 volts. You see that? See that? And then the same can be said when the voltage output is lower than our VEE, which in this case is 0 volts. So let me create a scenario where that is the case lah. So let's say now our V plus is actually 2 volts. Okay, so with all this information, what is V out theoretically? So we just plug in the things into the formula. 2 volts minus 4 volts equals, so that would be negative 2, so negative 200 volts, right? 2 minus 4, okay, calculator's not working. 2 minus 4, yeah, okay. So is the output, is V out going to be negative 200,000 volts? No, of course not. Again, the clamping thing is happening. So in actuality, right, it will be 0 volts. And let me show you why again with this graph. So it's V over T. And then it is getting clamped at 5 volts and ground is 0 volts. So 5 volts here, and 0 volts is here lah. 0 volts here. So let's say here, right, we power it on, and then theoretically output should be negative 200,000 volts, right? So this is negative 200,000 volts. But no, because it's clamped at 0 volts here, right? 0 volts here. So it cannot go any lesser than 0 volts. So blue, which represents the actual output, it will just be a line like this. There. Okay. So that is the op amp and all this clamping shenanigans. Alright. So I'm actually going to be, I'll talk about actual practical uses of the op amp. So you may have heard about, oh, I'm lagging. Okay, so you may have heard in my previous videos me talking about things like a voltage comparator for sure, but not a voltage follower, but I'm going to be talking about a voltage comparator and a voltage follower. So let's do voltage comparator first. So its function is in the name. It compares two voltages lah. And it does so, it operates in a way we just described just now. So the general rule is, if V plus is higher than V minus, then it will output a logic 1. If V plus is lower than V minus, it will output a logic 0. And then this here is a voltage divider. So we can just tweak. Oh, and I have a video about voltage divider. So if you don't know what I'm talking about right now, you should just go and watch that video. Alright, so and the purpose of the voltage divider is to like get the V minus. Okay, so let me just explain this in a practical way. Let's say we want to create a circuit where if V in is higher than 4 volts, then we want to have a buzzer sound, okay? And if it's lesser than 4 volts, then we do nothing. So very simply, right, we can just connect a buzzer. I don't know the symbol for buzzer, so okay, let's say a bulb lah. Okay. And then we just need to set the values here to get 4 volts, which I'm not going to do because I'm very lazy. So now, if V plus is higher than 4 volts, which would be like, let's say 6 volts, then the output will be a logic 1. Why? as I literally showed just now, the basically when you put these two values and plug them into this formula, with the open loop gain being a very high number, you'll get an extremely large number here lah. And it'll be clamped down by the voltages. I didn't draw it here, so okay, that may have caused confusion, so let me just draw it here. Basically, since it's a very high number, it gets clamped down, then the output will be what VCC is, so, and that will be logic 1 lah. And then if instead of 4 volts, it's like 2 volts, then it would be, again, this multiplication stuff will happen, the output will be like negative 2 billion volts or whatever, and it'll be clamped down by VEE, which in this case is 0, and 0 is logic 0. So that is what a voltage comparator is. It literally just did everything that we asked for. So if okay, yeah, that's it, yeah. Alright. Okay, and then now voltage follower. So, okay, these names are pretty self-explanatory. A voltage follower takes the input and then it outputs the input. So that may sound like kind of useless, but for delicate circuits, it is very useful. So what do I mean by that? Let's say you have this circuit, and I'm just going to put like a box or whatever. C for circuit. And then let's say this is the output. So then you like take a multimeter and all, right? And then you go and measure it, and then you see, oh yeah, it's periodically producing 5 volts, 0 volts, 5 volts, 0 volts. So this is pretty much just a 5-5 timer. Okay, let me change this to say 5-5 timer. So let's say it is outputting 5 volts to 0 volts to 5 volts every 1 second. So then you say, okay, this is a multimeter, by the way. So then you go, oh, okay, this is doing what it's doing. Let me connect this to an LED. And then you ground it. And then disaster strikes. Immediately, when you put the LED, right, the period at which it changes from 5 volts to 0 volts to 5 volts decreases all the way to 0.1 seconds. So what's going on here? Basically, right, this circuit, this 5-5 timer circuit, or this oscillator circuit, basically is very fragile. When there's a load, when it gets loaded in its output, right, some of the components inside immediately drain out their voltage because it has to power the LED, and as such, it does not function as how it should be. So what the voltage follower does is it removes this level of uncertainty from this very fragile chip. So how we use it, right, is we have this chip here. We just bring this to the input here, and then at V out, then we get the LED. Then we ground it. Okay, ignore this is, you shouldn't put your ground on top lah. But then we ground it, and then this is now fine. So if we power everything on, it's gonna be 5 volts to 0 volts to 5 volts to 0 volts 1 second, it will stay the same. So what the voltage follower does is it just removes the load on this on the fragile bit of the circuit, and then it just handles the load for the load. And I'm not going to explain how it does because I'm lazy, so let's move on. Okay, so I've actually talked about the op amp and some of its uses. And I have 2 more uses to go through. And it involves a configuration of the op amp. So I've just showed you 2 like configurations, bunny ears. One is the voltage comparator, one is the voltage follower, but they're not really configurations per se. You're just like kind of adding stuff to it. Okay, I don't even know what I'm saying. So I'm going to talk about the inverting op amp and the non-inverting op amp. Okay, so here, this is the inverting op amp. What does it do? Yeah, what does it do? So basically, right, The op-amp can be used to amplify AC signals. So what is an AC signal? If you don't know what an AC signal is, yeah, I have a video talking about it, so you should go watch that now. But basically, right, like an AC signal is just a signal that goes from positive voltage to negative voltage periodically lah. So this is an AC signal. And what the op-amp does is it takes in that signal and then it can output it amplified. You see, the peak-to-peak voltage here is higher, much higher. So this is one way of configuring the op-amp to amplify the V-in lah. And this configuration is the inverting op-amp, inverting amplifier. So what it does is it takes in this signal, it shifts it 180 degrees out of phase, and then it amplifies it. So I said a lot of words that may not seem to have meaning. So let me just draw out what happens. This. So you can see right, at this point of time, oh yeah, and this is V, this is time. At this point of time, it's supposed to go up, but basically it goes down. So it got shifted 180 degrees out of phase. You can just think of it like you have a coin that's heads and tails, right? You just flip it upside down. You just flip it upside down. So basically here, we're just flipping it upside down. And then the not amplified inverter signal will look like this. So you can see it's just the opposite of what is purple. V in lah. Then it amplifies it, so the peak-to-peak voltage increases dramatically. Yep. And then here is how you can configure it. Okay. So how exactly, right, do we calculate the gain? You know what I mean? Because we don't have a lot to go from here. But I'll go through that in a practice question. So for now, just accept that it works. Yeah. And this is the gain. So basically, to amplify this signal and invert it, right, by like this much, we can use this equation here to find that amount. So and it's called that amount is called closed loop gain, and you get that by here lah. So you just sub in this resistor here, this resistance here, and then like minus. Bruh. Okay. So next is the non-inverting op-amp. So in here, right, instead of, okay, again, it's in the name. Instead of inverting the signal, it doesn't, and then it just amplifies it. So that's pretty much it. And then the equation to get the closed loop gain is 1 plus RF divided by Rin. Yeah. So, oh yeah, and this stuff you need to memorize. Yep. One thing to note is that I've been talking about all these op-amps with the plus and minus. You may not have noticed, but for the amplifiers, for the inverting and non-inverting op-amps, right, the minus is actually on top. And this is actually very important because if you get this mixed up, right, like it's not going to work out well for you. Yeah, and you're going to get everything wrong and then you fail. So yeah. So yeah, that's one thing to note. That's also pretty important. So now let's actually move on to this practice question. Okay, so sorry. Okay. So calculate the gain. Oh yeah, yeah. Let me read this first. Calculate the gain of the non-inverting amplifier shown in the figure. Sketch and label the input and output sinusoidal waveforms given that the amplitude of the input waveform is 1.2 volts. Okay, translating that to English, what it's saying is V in here, right? V in there is this. So this is V in. This is time. It's saying there's a sinusoidal waveform, and the amplitude is 1.2 volts. So this is negative 1.2 volts. Okay, then we need to get the output. So now, since you know that what Vin is, because it was a bit hard to find, because like you've never seen. Alright, you can pause the video now to try and find what the output is lah, and you have to sketch it, yeah. But I don't think you can, because I didn't really explain how to even apply, like, okay, let's just go. So if we just analyze this a bit, right, you can actually notice that this is a non-inverting amplifier. See, if we look at this, it's the same configuration. So we can actually just find the closed loop gain using the non-inverting amplifier equation. So this would be RF, this would be 1 plus RF divided by R in, and then this would be 1 plus 22 kilo ohms over 22 kilo ohms, which is 2. Okay, so what can we do with this? Just now, just now I said that it will relate to like this thing. Hold on, let me just draw a separate V out. So how to actually find the how much it amplifies by? You take the original amplitude and you multiply by 2. So you see the amplitude here is 1.2, right? You just need to take 1.2 times 2. So your new amplitude is 2.4. So here is 2.4 volts. Here is negative 2.4 volts. Yeah. So that's that. Yeah, okay. Let me give you an actual practice, because this was kind of mid. So I'm gonna make a question on the spot right now. Okay, so this is the question. V in, right, is a square rectangular waveform. It is a rectangular waveform AC with an amplitude of 6 volts. Okay, amplitude of 6 volts. With this information, find V out. So you can pause the video now to go ahead and try. Oh, no, yeah. Sketch the graph of V out. Okay, so analyze the circuit first, and then you'll see you see that this is an inverting op amp, because it's the same as this one. So the equation to get closed loop gain would be negative RF over R in, and then we just get, and then this would be 3 ohms over 7 ohms. And if we plug this into a calculator, we'll find that okay, I'll just say that the gain is negative 3 over 7. Alright, so now armed with that knowledge, we actually already know how much is going to be amplified by. So let me draw the graph for V in. Alright, so this is V in. Okay, V over T. Green is going to be V in. Alright, so V in is a square wave. So it'll look like this. Okay, and then this here, since the amplitude is 6 volts, right, then this would be 6 volts, this would be negative 6 volts. Alright, now let's have red represent the output. So our new amplitude, the new amplitude would be the original amplitude times negative 3 over 7. Or we can pretty much ignore the negative, but let's just include it here. So our new amplitude is negative 18 over 7. Let's get like an actual number for that. Okay, 2.57. 2.57. Huh. Yeah, 2.57. So it actually decreased. It did not amplify the AC signal, the AC amplitude. It decreased the amplitude. So our new waveform will look like this. It will look smaller, and it'll be inverted, as you can see here. So then this would be 2.57, and same here, negative 2.57 volts. So yeah, that is that question. So that's pretty much it for op amps, voltage comparators, voltage followers, non-inverting and inverting op amps, yeah, amplifiers. So yeah, that's that. Sorry if this lesson was a bit chaotic and I'm a bit sick, so yeah, okay. That's it.